Welcome students, everybody, to the experimental testing for aerospace structures. Today we are going to start our class with the students' opinion questionnaires. I know that most of you know what's the meaning of these questionnaires. However, just to resume the basic facts, we as all the Italian universities are evaluating our student activities and teaching activities through these questionnaires. And because of that, you are kindly asked to fill in these questionnaires in order to have a sort of evaluation of the course. Okay. In our analysis, in our course, we don't have different modules, so we just having one module, that is the aerospace structures course. The code of this, the office code of this course is available at your email that I'll send you for the to give you the link, the Google Meet link for today's class. Okay. So you have to take note of this code that I wrote you in the email. Okay, and then assess your InfoStud pages. Okay, and here is how you can enter. So this is the login. Okay, so you have to enter with your InfoStud login. Okay, details, matriculant password. Then you have to choose the degree programs. Okay, and then select corsi di laurea, and then student options. Okay, and then go to the questionnaires, this bio questionnaire. Once you are there, you have to select the course. Okay, and then provide all the answers, okay, that you think are suitable with your with this course. Okay, I thank you very much for your feedback. As you know, this figure is complete anonymous, so you can write whatever you think it is good to know to read in order to improve the course itself. Okay. The only thing that I'm asking you is to be honest with you. So in order not to have false information from your side, and also in order to have a good improvement, real improvement for the course and therefore the whole university activities. Okay. I think that you can start. You got 15 minutes. Okay, about 15 minutes, no more than that. If you have any issues, you can say to me right now, or you can just write a message in the Google Meet message board. Okay. So please start your questionnaires.
Excuse me, Professor, which code we should use for going to questionnaires?
You should use the code that I wrote you in your email, but however, I'm just writing in this message board. Here it is. Oh, can you see it?
Yes, thank you.
Okay. Okay, I think that you complete your questionnaire. If not, you can do that at the end of the class today or other days. And so we can start our class. And let me start recording the call. Okay, so last Tuesday we start analyzing the method that is operating in the frequency domain that is called least square complex exponential method. Okay, just a brief recap of the method. We had the hypothesis of the linear system, and the system dynamic was modeled in terms of the impulse response functions, as we can see in the equation, in which we can assume that the index, k index, is derived from 1 to the double number of sampling points, because we are considering also the complex and conjugate parts of the residual terms and the poles. Okay, then we move and then we define the HL. Okay, HL, and this HL is the impulse response function evaluated at the else time instant. I'm dropping, of course, the indexes of the ij components, and so we refer to the summation sign from k that goes from 1 to an n of the AK BKL. And on Tuesday, I'll give you the meaning of the VK, okay, and the AK. Now, please remember that in our method, what we are having is that these terms, the AK, the other terms, the BK, and 2n also are all unknowns. Okay. These are all knowns, and the method, the complex exponential method, is willing to identify those unknowns. How we can do that? So the methods introduce the solution of the equation h beta times negative h tilde, okay, vector, okay, and therefore solve, of course, for the vectors of unknown beta. Remember, those are the coefficients that we fictitiously introduce. So we have beta 0, beta 1, up to beta 2 and negative 1. Then we got the matrix of the pulses of functions. These, of course, are all quantities that are very well known, because this comes from the inverse Fourier transforming of your frequency response function that have been already identified when performing the H2 or H1 or whatever estimating method to your input and output data. Okay. So that is your H, and the last part, the last vector, is the vectors that we consider as known terms, H to n up to H for n. Okay, so once we found these betas, then the procedure, is try to find the v vector, one of the unknowns, okay, from the roots of the algebraic equation that includes your betas that have been just identified from the previous step. Okay, square up to the very last term. Okay. Then once we got these V terms that are the roots, okay, of your algebraic equation, then A from the system that has been written as B A equal to H. Remember, your B matrix is 1, 1 up to the last term, B1 up to the last term, and then the last contribution is B1 to 2 and negative 1, 2 and 2 and negative 1. Okay. A, of course, is the vector of unknowns. So A1 up to A2n. And finally, H is H0, H2n. Okay. So that is our solution scheme, if you want, in our analysis. Now, the problem is the one of solving for the unknowns and also solving for n. So how can we solve for it? The solution of this problem comes from the observation that we can have whatever system order that is, we can choose between different values of the index n, and according to this choice, what we got, we have several solutions corresponding each to n that has been chosen. Okay, so for example, if we are having n equal to 1, then we have just one solution, one constant conjugate solution actually. Okay, then when we are choosing n equal to 2, we have 4 solutions, that is 2 solutions in the real part, and so far, and therefore we can have a lot of solutions. Now, as you can see from this equation, the modal model, sorry, in terms of A, the residual terms, A, ij, kth contributor, and the pole lambda k, is not depending, okay, on the other terms. So it's not depending on n itself, okay? So what I can say is that in order to solve for n, it is observed that aijk and lambda k do not depend on n. Okay, so in on the summation index k. Okay, and that observation brings me important information. That is, I can think to iterate the previous procedure. So from, let's say, 2 up to 4 by increasing the model order. So as a result, the procedure 2 to 4 is iterated until is iterated by increasing the model order until convergence is reached. What does it mean that? It means that we are starting that procedure here from the very beginning, just by assuming the system having n equal to 1. As a result, we will have a set of poles and set of modes, okay? And then we increase n from 1 and 1, 2, 3, 4, and we go up until what? Until we can find out that there is a suitable number of model parameters that are no more dependent on the index itself, that is, on the mode order itself. Okay, that is, we are evaluating the poles of the system through a stabilization diagram, as it is called. Okay, that is, we are increasing the model order, to which model order a certain set of model parameters will be identified, and those parameters are in general different from one model order to the next one. So what we are doing by iterating, that is by increasing this n, that is the model order, we are going to look if there are some orders, model orders, in which the model parameters are not changing, okay, by increasing the model order. If that is true, it means that your solution is not depending on the model order itself, okay? And therefore, if the solution is not dependent on the model order itself, then we are in the physical condition. That is, what we are having is that the solution of that approach is representing a good approximation of your physical poles and modes, your physical model parameters. The other solutions are just mathematical solutions that are not good for the physical representation of the system properties. What is done generally is the building of what is called a stabilization diagram. In this stabilization diagram, what we are having is a two quantity, completely different quantity that are plot one over each other. Let me show you how the stability diagram looks like. So stability. So what we got here is the representation of the FRF. So let me have this. So for example, we have frequency and then the amplitude of your FRF. Now, the first question is which FRF we have to consider. Remember, when you are down in the laboratory, you have a set of pairs of indexes, A, I, J, okay? So what we are doing here is plotting as a first side, then we can go into more details if you want to solve some doubts, if you have to enter into more evaluation of some specific behavior in certain frequency range or for certain model parameters. But in our analysis, that is the first approach analysis, what we are having is the average FRF amplitude in this case, okay? And that because by using the average FRF, we can have the information of all possible poles that are active in your structure without going to the risk of neglecting some poles because that specific FRF is not containing any poles that are interested, which we are interested in. Okay, so that's the reason why we start with the average. Then I'm plotting the corresponding FRF. Oh, sorry, I don't like that. For example, that one. Okay. And then we are plotting on the, let's say, right y axis, that is on the additional axis, like this, for example, your model order n. And this is done by having different model order lines like this, for example. Okay, this is the model order 1, 2, and so on. Okay, and you get up, up, like this. Okay, you can have several horizontal lines. Okay. Then what you are plotting is the solution of your complex exponential method algorithm to these corresponding to these horizontal lines. What does it mean? Let's assume that we have having 1, 2, 3, 4 up to whatever order. Okay, so if we are applying your complex exponential method with your model order equal to 1, the algorithm maybe is telling you that here is your solution. Okay, for example, this. Then you redo the analysis by increasing by 1 your model order, that is, we are going to 2, and maybe what you are having is a solution like this. Okay, then increase once again, we are having 3 solutions, for example, one like this and the other one like that. Then increase, okay, let's have like this, for example. Okay, and maybe we can have some other points over here. Okay, just by increasing your model orders. Okay, so as you can see, there could be some poles. Oh, by the way, these circles represent the imaginary part of your just identified poles. That is your frequency, if you will. So you can see that, for example, just by looking at the peak number 1, the first one, we are having that starting from the lower model order, that is 1, we are, by increasing this model order, we are having that the poles is sort of aligned with your peak, okay? Also, when you are going up with the model order, are some poles here that are aligned with the second peak, and therefore also for the third peak there is an alignment, okay, with the third peak. Okay, what does it mean, that picture? Now we are having this stabilization diagram that is telling me for a given pole what is the model order corresponding to that model parameter, and we can also identify your pole of the system itself, because when you are up to a very good approximation of your just identified solution with the peak of resonance, then you can choose your own pole, and that is your estimating process, okay, estimation process, okay. Here, in order to improve the capability to distinguish between good poles with respect to the bad ones, what we are saying is that if we are using this circle here, that is, we are telling you that you have just identified a pole, okay? Let me write it a different way. Pole is identified. Okay, then if we are using, for example, a V, what we are saying is that the pole at the model order n, okay, negative, the pole at the model order n and -1, that is at the previous one, okay, in amplitude is less than a prescribed quantity, okay, tolerance. Okay, if you are having S, then you are saying that the real part of the pole at the end model order compared to the real part of the pole at the model order just below and is practically less than the tolerance, and the imaginary part of the same pole compared to the corresponding imaginary part of the pole just at the model order below is less. Okay, that is what we call a stable pole. Okay, and for example, in our analysis, what we can say, let me change this, for example. Oh, okay, can we do this? And maybe here we got a V, okay. Then let me increase a little bit. Let me see if I can. No, I can't do that. Okay, so maybe we can have an S pole over here. We can do the same here, B and then S. Maybe we are having B, V, and then some S's here. Okay. That is telling you that your criteria for which the identified poles are not dependent on the system order is satisfied by using the, let's say, worst condition, that is the more critical one, that is a stable pole. Okay. By the way, if you are increasing your model order, that is, if you are using n that is much larger than the system, the actual system model order, then there could be some numerical instabilities, and therefore what you can have it maybe is a lot of poles that are characterizing each stability line, so model order line like that, and therefore you can identify poles. Okay, so what we say is here numerical instability when n is higher than model order, no more than physical model order. Okay, that's what could happen. And therefore, here comes you, that is the person that representing the person who is responsible for the identification of the model parameter, for the estimate of model parameters. Okay, so there is not a rule of thumb that could be applied whatever. Okay, so you have to choose between the different poles that your complex exponential method is telling you, and you have to choose that by using this stabilization diagram that you can see here. And generally, what you can say is that you start looking at the stable poles as pole across the peak of resonance of your FRF, okay, and therefore try to see when you got some poles that are in columns and the algorithm are in stable conditions. Therefore, you can choose the lowest order poles if the modes of your structures are well separated. Otherwise, you have to go increase your model order in order to choose your stable pole, because it is expected that the model order is higher with respect to clear and neat single degree of freedom harmonic oscillator. Okay. And by the way, you can have also that corresponding to different modes, you have different model orders. Okay, so mode order number one, for example, the stable pole corresponding to the first mode order is we are having it at lower level with respect to the stable pole of mode number 2 or mode number 3, as you can see here. Okay, so it depends on the mode itself, and And of course, the reason why is that they could have different coupling between adjacent modes corresponding to the mode order itself. Okay, that's it for today. Time is practically over. Questions, please? Okay, if there are no questions, thank you very much. And I wish you a very nice weekend. See you on Monday. So Monday we will have class as usual. Okay, same time as the other classes. Okay. So thank you very much.
Arrivederci.
Arrivederci.